All right, so we're going to look at area under a curve, and we're introducing the concept of integrals. Now, the problem that we have, and this is one of the things that is kind of behind the development of calculus in the first place, is trying to find this area under a curve. I told you that derivatives, when they were originally trying to discover the derivative, the whole point was because they were studying optics, and they were trying to find that normal line to a curve. And in order to find the normal line, you had to find the tangent line, and which led to our derivatives. Well, here, the idea was, how do we find the area underneath a curve? Okay, and Archimedes actually originally had a, came up with kind of what we're going to look at today. Obviously, it was expanded upon, and I believe it was Leibniz actually came up with the symbol for integration, as well as a lot of our other notation. But we were looking. Sorry. That's all right. You're taking pictures, right? As well as a lot of the other notation for our calculus. So the idea is this: we're trying to find the area between the x-axis and the curve along a specified interval, in this case from 1 to 4. Okay? The problem is, obviously it's a curve. Alright, it's not a straight line. So a number of different ways have been developed to approximate this. Okay? So we're going to look at a couple briefly. We're going to kind of summarize it, look at a little bit of notation, and try one of these. And then we'll relate this to the integral itself. And I want to also mention a couple of methods your book does not deal with for approximating area, because there are a number of different ways that people have come up with in order to try to approximate area. All right. The first way, the first two ways really, are using upper and lower rectangles. Okay? Upper and lower rectangles. Now, what are we talking about when we're dealing with upper rectangles? Well, basically, the idea is this. We take the interval that we're working with, and we cut it into strips of equal width. Okay? So you'll notice I made rectangles here, and each of those has a width of 1, okay? Now, with our lower rectangles, we do the same thing. From 1 to 4, we cut it into 3 equal strips. Each of those has a width of 1. The difference in these two methods is which side of the rectangle, or of the interval, I should say, you're going to draw your rectangle up to. Okay? So for our upper rectangles, notice this is increasing. We're going to go to the higher side of the two. Okay? So in this case, on the right-hand side, it's higher. So I'm finding the area of this rectangle. Okay? Now, how do I find how tall this rectangle is?
14 times the height, like the length times the height.
How do I find the height? Did I say area?
Oh,
sorry.
Just looking to the left.
Looking on the right-hand side here. Okay. How do I know how high that is?
Just like drawing a line to the left, like to the axis.
Okay. So we draw the line over here to the axis. We see it hits at 5. Okay. That's true. How would I use my function to do that?
You plug the x in.
Yeah, plug the x coordinate in. Here I'm using 2. So the height of this rectangle is f of 2, which in this case is 5. Okay? Does that make sense? So, my first rectangle, the area, I'll call that area 1, the area is width times height. Okay, so 1 times my height of 5, so that equals 5. Okay? Then I need to do that for my other rectangles as well. Okay? Here's this rectangle. To find the height of this rectangle, I'm going to take f of 3, which in this case is 3 squared plus 1, so that's 10. So the second rectangle is, my width is still 1, my height is now 10, so the area there is 10. Okay, then I would find the area of my last one. Okay, so now I'm taking f of 4. Okay, f of 4 squared is 16 plus 1 is 17. So width times 17 is 17. Okay, so I would then approximate the area under this curve to be, A is approximately 5 plus 10 plus 17, okay, or 32 square units. Okay? Now, what can you see as the problem with this method?
Triangles. Like it's not exactly underneath the curve.
Okay, it's not exactly under the curve. In fact, is this area that we just found going to be bigger or smaller than the area we actually want?
It'd be bigger.
It's going to be a lot bigger, okay? In fact, we've got this area here, we have this area here, okay, and we have this area here. Now, there's not a good way to get rid of that because, again, one of the sides is curved, all right? Now, if we come over here and look at the lower rectangles, okay? By the way, this A is often, they'll use A sub U for the area of the upper rectangles, okay? We can find the area of the lower rectangles to approximate our area. Notice the difference here is that instead of using the right-hand side of each interval to make our rectangle, we use the left-hand side of each interval. All right? So now instead of doing f of 2 to get my height for that rectangle, I'm doing f of 1. Okay? And that equals 2 in this case. All right? So my first area is the width times 2, which is 2. My second area is going to be my width times f of 2. And f of 2 is 5 again. So that's 5. And then thirdly, I do my width 1 times f of 3. Okay, so 1 times 3 squared plus 1 is 10, and that equals 10. Alright, so my total area here for my lower rectangles is 17 square units. Okay, now, as far as approximations go, we have a pretty huge range here of possibilities, from 32 down to 17. And I know the area I actually want is somewhere between there. Because this one is actually less. We left out some pieces. We needed this part, okay? Yes, Cameron?
Couldn't you use the first one and just subtract the triangles? And you get a pretty close estimation of the area?
Well, we could, except notice these triangles. This side is the curve.
Okay.
That's a curved part. So we kind of have the same problem that we did with the original problem, is the fact that we don't have straight sides. Otherwise, yeah, we could use some kind of a polygon method of finding area.
What if you use the first one, subtract the other one, and divide by 2, and then add it up to the lower rectangles, or subtract it from the upper rectangle? Like you would get the curve, and then the curve on the upper hand side, and then you subtract one from the other. And like you just subtract the upper rectangles from the lower, and you just get the square.
Yes.
And then you divide by 2, and then you just get one of them.
And that actually is a great idea. And really what you're doing is you're averaging the upper and lowers. Okay? You're finding the mean between the upper and lower. That actually will give you the same thing that you would get using one of another method that people use. And that is, rather than using upper rectangles or lower rectangles, one of the things that folks will do, which does give you a closer approximation, is they break it into intervals again, but instead of using the left-hand side or the right-hand side, they use the middle. Okay? So my height for this rectangle, I would be making the rectangle like this. And you'll notice the advantage to this is I would have a little bit extra right there, but I would leave out a little bit over there. Okay? So you're counting a little bit that you shouldn't, and you're leaving out a little bit that you should include, all right? And you get a little better approximation. Okay? There you're finding, 1 times 1.5 plus 1 times, or I should say not 1.5, 1.5, f of 1.5. Okay, plus 1 times f of 2.5, because that'll give me this rectangle, right? And then here, if I do the middle again, that's going to be 3.5 for my height, f of 3.5. 1 times f of 3.5. And that's another method that folks have used to approximate the area. And that actually does give a bit closer of an answer. If I average those two, I get 24.5, which is what we would get if we did this. Okay? And again, it's because it's easiest to see here. I'm counting this when I shouldn't, but that's approximately the same size as this little piece up here that I didn't count. Okay? So, that's another way we can use the middle rectangles, okay? I think there's a name for them, but I don't remember off the top of my head, okay? Another way is using any of these 3 methods, okay? But how could I make it more accurate, do you think? Using upper rectangles, let's say. How could I make the upper rectangles estimate a little more accurate? What do you think? Is there something I could do in this whole process that would eliminate some of the extra stuff that I have on the outside? Any thoughts? What if we cut it into more pieces? Let's look at what would happen. If I, instead of cutting it into 3 strips, what if I cut it into 6 strips? Okay, so there would be a rectangle, and then here would be a rectangle, and then here would be a rectangle, and then here would be a rectangle.
But wouldn't be this like almost the same as the middle rectangles? But we would still have the we would still have an additional space.
We'll still have some additional space, okay?
We have more space because we're increasing. It's not as even as the middle rectangle because we always have a little bit more on the outside of the curve.
Yeah, we'll have a little bit more. The middle is going to give us a better approximation in general, okay? But what we're doing here, actually, whether we use upper, lower, or middle rectangles, okay, doing this will make that method more accurate. By cutting it into narrower pieces, notice what happens here, okay? We end up, we had been counting this, and now we're not, okay? So look, we have less extra than we did originally, okay? So we now cut off some of that, and now we cut off some of that, all right? Now, how could we minimize this even more?
Well, you could have more, like rectangles.
Yeah, have more and more and more rectangles.
I also noticed that for the middle rectangles, the value that we got was exactly in between the upper and the lower.
Mm-hmm.
So could that, I mean, I guess it's a longer way, but I guess if you find upper and lower, then you just meet in the middle and get that approximation. Would that work?
Yes, it would. It would.
Mr. Hickson,
Mm-hmm.
I was going to ask you, how do you get those results, for example, for the middle rectangle, just from the, like, is there a way, like, you know, in derivatives we would find the slope from the function itself? Can we do it other than plugging in the values? Like, for example, you don't get the graph,
Yes,
and you don't sketch it, and you want to find
the
the
integral.
integral.
Yes. What we're going to learn how to find integrals, and that's what it's going to do for us. But the reason why we're going through this is because I want you to understand what the integrals are actually giving us, okay? And if you guys take AP Calc next year, one of the things you'll look at actually is the trapezoid rule, and using Riemann sums, where you're doing this, and there actually are some functions where this is the best we can do. There isn't a nice rule for integrating for that particular function. So we would have to use some kind of a process like this to approximate the area. Okay? So what we see here is we could have, you know, a lot, the more rectangles we have, notice the smaller the width is going to get, okay? So let's say we let n be the number of rectangles. Each of these intervals, oh wait, I need to get off the white marker. Each of these intervals, okay, is going to have a width equal to the right-hand side of our interval 4 minus the left-hand side, because that tells us that our interval is 3 units long, okay, divided by n, however many rectangles we want. Okay, so if we wanted 100 rectangles, we could do 3 divided by 100 and get 3 100ths as our width. Okay, now doing 100 rectangles by hand would be a real pain. Okay, but that actually is where we can use technology to help us out. Okay, in fact, I did this problem. Remember I said the middle rectangles give us a much better approximation? Okay, well take a look at this. If I did the area of each of these little rectangles, okay, this is what the height of the first rectangle would be, 2.0609, if I cut it into 100 little rectangles. Alright, the first rectangle would have a width of 0.03 and a height of 2.0609. So its area would be 0.061827. Alright, super tiny. But notice the height in each case is going to be changing because our function is going up. Alright? So these are all the 100 rectangles we cut it into. And what did we get for the middle rectangles?
24.5.
24.5 as an approximation. Well, check this out. When we use 100 rectangles, we get 24.23. Okay? So the middle rectangles, even with only 3 rectangles, gave us a pretty decent approximation. Okay? But you can see here how it'll converge onto other values. Okay?
Mr. Jackson,
Yes.
like I tried to calculate the thing that I talked before about like one upper minus the lower and divide the value by 2, and I got 23. So which one is right, or which one is at least the closest one?
Well, hang on. If you
Like
subtract these two, you'll get 15 difference.
oh.
So then you
Never mind.
divide it by 2 and you get 7.5.
Never mind. I thought it was. I didn't like add them up, and I got like for some reason 14.
Oh, okay.
Yeah.
Okay. But anyways, let me just kind of summarize this whole process. Okay, what we're really doing, okay, is I already mentioned this 4 minus 1 over n. It's going to be 3 over n. That's going to be the width, dependent on how many rectangles we want. And our height is going to change based on where we are. We start at 1, and for the first interval, we're going to add that 3 100ths. And then add 3 100ths, add 3 100ths, okay? Now, we need to add 3 100ths for every rectangle, okay? So what we actually would be doing is we would be taking the sum from I equals 1 to n, okay? Add up however many rectangles we have, and here's just our width, 3 over n, times the height. And you'll notice here I put an I in here for our sum. This isn't square root of -1, this is for our sum, because every x coordinate is going to increase one more interval. Okay, so for the first rectangle, we're just going to be adding 1 plus 3 over n. Then for the second rectangle, we need to add another 3 over n, and then the third, another 3 over n. Okay? So, we already said, if we make it 100, we're getting an even closer approximation. Okay?
Where do we get the 3 from?
That's how wide our interval was, because we went from
So
1 to
it's-
4.
It's based on the interval.
Yeah,
So it's not
it'll-
like this is for every.
Yeah, it's not every problem, it's 3, but whatever your interval is. So what we did is this right here. We went from 1 to 100, okay, and this is how we got, on the spreadsheet, we got that 24, what was it again, 24.225. Okay.
What is I?
I is the counter for your for the sum. So the first rectangle, second rectangle, third rectangle, fourth rectangle, up to 100. It's just moving your x coordinate over one interval at a time.
Okay.
Alright. So what do you guys think would be a good idea to do, thinking about our calculus, in order to get the most accurate approximation possible? We want more and more and more rectangles, right? So what could we do?
Infinite.
We could let the number of rectangles approach infinity. So we'd be taking a when you let a value approach something, huh?
Limit.
A limit, yeah. Okay. We'd be taking a limit, alright? This right here, now this isn't technically a Riemann sum, because Riemann sums use the middle rectangles, but this is kind of like the Riemann sums. But notice here, I said 3 was how long your interval was, okay? If your interval is from A to B, we're simply replacing the 3's with B minus A's, okay? Because that'll tell you how wide your interval is, and then you're dividing it by how many rectangles you have, okay? And that really is the definition of an integral, okay? At least using the upper sums, or the upper rectangles, okay? Now, we're not really going to use that per se. We're going to learn the rules for integration, but I want you to see kind of where all this is coming from, okay? So let's talk about what that would actually tell us, okay? What does that actually tell us? That gives us what's known as the definite integral of f of x, okay? The definite integral. The reason why this is known as the definite integral is because it's over a defined range. It's from A to B. Alright, now note notice what we're actually finding the area of. Here's some value A on the left, here's some value B on the right. Okay, and we want the area under the curve in that interval. Okay? So we have the interval from A to B, and this is the area that we're trying to find. Okay? Now the notation here, this symbol here for integration is an elongated S. Okay? And we would read it, the integral from A, you always put the left-hand side of your interval on the bottom, to B, that's the right-hand side of our interval, of f of x dx. What that tells us, remember when we did our derivatives, you had dy dx, and dx told you what variable you were taking the derivative with respect to. Here, this again tells us that we're integrating with respect to x, in this case. Alright? So the integral from a to b of f of x dx is how we would read that. Alright, so let's work through, we have just enough time I think. Let's work through one of these real quickly here. This is kind of a simple one because they give us a function. It says, consider the area between the line y equals x. So that's a nice easy function to work with. Okay, y equals x. And the x-axis from x equals 0 to x equals 1. So I'm going to put 1 here. Okay, and this is our point 1, 1. Okay, now if you were given this on the IB exam and they just said find the area and they didn't say how, what would you do? You would not use integrals. It's a triangle, right? So the area of a triangle is 1/2 base times height. The base and height are 1 and 1. So 1/2 times 1 times 1 is 1/2. Okay? And you'd be done. Alright, when I did my IB training last summer, we were doing a sample exam, and they actually gave us one that wasn't like this, it was a trapezoid. And I was focused on calculus and did the whole thing with integrals, and then stopped and said, you dummy. Could have just used the formula for a trapezoid. So don't miss some of those easy ones. I wasted 10 minutes on one I could have done in about 10 seconds. But anyways, let's take a look at how we would work through this. Alright, it says divide the interval into 5 strips of equal width, then estimate the area using upper or lower rectangles, okay? So if I divide it into 5 strips of equal width, and I'm going from 0 to 1, how wide is each one going to be? A fifth, okay, or 0.2. Alright, so there's 1/5, 2/5, 3/5, 4/5, and obviously 5/5, okay? So each of those has a width of 1/5, okay? Now, if I'm using upper rectangles, let me make this a little thinner, okay? Then I'm going to be finding the areas of these rectangles here. Okay? So let's do that. The area of the upper rectangles is going to equal, I have 1/5 times, what's the width of, or what's the height of my first rectangle? Where this is the line y equals x, so
What's the
1/5?
1/5. So that, no,
1/5?
it'd be 1/5. Okay. Alright. So that's the area of my first rectangle. The second rectangle also has a width of 1/5. But what's its height? Yeah, I go another 1/5 over, I'm at 2/5, so the y coordinate's 2/5. Okay? My third rectangle is going to be 1/5 times 3/5 plus 1/5 times 4/5 plus 1/5 times 1. Okay? So, especially if I make this 1 into a 5/5, I'll have a common denominator of 25. So let's look at what all my numerators equal. 1 plus 2 plus 3 plus 4 plus 5. Okay? So that's 15 25ths, which is 0.6, or 3/5. Now, is that close to you, or close to what we knew it was supposed to be? Yeah. Okay, but it is a little high. Alright. So let's try it again with our lower rectangles. Now look at that first rectangle. What's its height gonna be? 0. Okay. So that's our first one. Then there's our second, our third, our fourth, and our fifth. So what we actually end up with our lowers, we end up with 0 plus 1/25 plus 2/25 plus 3/25 plus 4/25, and that ends up giving us a 0.4. Yeah, it ended up giving us 8/25. No, 10/25, sorry. Which is 0.4. You'll notice if we average these two, we would actually, in this case, get exactly what the area was. Okay? But here you see how they can relate to each other. Alright? Alrighty. Have a good day. See you later.